Okay guys, so this is the continuation of the first part of subtopic 2.4, determining key features of the graph of a function. Now I already showed you what the intercepts were and what the symmetries were. Okay, we haven't yet talked about the local and global maxima and minima. I'm gonna delay that a little more, okay? And you will know why. Okay, that's gonna be for part 3. So let's get into getting the intercepts and the symmetries of the function by means of analysis, okay, without really looking at the graph. Anyway, I'm gonna put the graph here, okay, but that's just gonna be for reference, okay. For example, we have 5 functions in here. We're gonna analyze the intercepts and the symmetries of each of these functions. So this is the first function, f of x equals x squared minus 1. And we already know right away by looking at the graph, we know that the y-intercept is this one, minus 1. Some people say that the intercept is just the value at which the graph crosses the y-intercept, in this case minus 1. And some other people actually say the whole number, okay, like the both coordinates. They say that the y-intercept is 0, comma minus 1. It's basically the same, okay, it's equivalent, because all the y-intercepts obviously have to have uh, an x value of 0 in the first coordinate. That's obvious. All of these points along the y-axis have 0 as their first coordinate, as their x coordinate. That's clear. So this is like redundancy, okay? And for the x-intercepts, we have minus 1, which is this value, or minus 1 comma 0. Some people are going to tell you that. And the other x-intercept is 1, or 1 comma 0. Okay, all these points, all these any x-intercept has to have as its second coordinate 0, because all these points along this x-axis obviously have their second coordinates 0, all of them. So it's redundant, but anyways, I just wanted to tell you that. Okay, so we know already the y-intercept, sorry, and the both x-intercepts. Now let's get them analytically, and you will see that it's very, very easy. So let's start. The first thing you want to do is the following. You want to place again, or put this function in this way. Again, you're going to transform the f of x into y. Remember that we can always do that. So there you have it. That's the first thing you want to do. And then for getting the y-intercept, I write it here. What you have to do is make the x equal to 0. You're gonna assign the value of 0 to the x in this function, and you're gonna see what you get for y once you do that. So let's do it. Y equals x squared, but remember that we're gonna replace x for 0 minus 1. We continue with the solving of the equation. Y equals 0 to the square is 0 minus 1, and then we have that y equals minus 1, and we're done. This is the y-intercept. There you have it. Can you see? Minus 1. And again, some people are going to tell you that the y-intercept is 0 comma minus 1, a point. Okay, both of them are fine. Both of them are equivalent. Okay, there's no ambiguity. Whether you just say the value in the y-axis at which the graph crosses, or the whole point, that's okay. And that's how you do it. You make x equals 0 in the function. Now why does it have to be x equal to 0? For the same reason I told you. In order to find at which point in the y-axis the graph crosses, that means that for that particular value, x has to be 0 again. Okay, this value here, just by looking at it, you know that the x coordinate of this value has 0. Okay, it has to be 0. That's why when you make 0 in this equation, you're gonna get a value of y that will be the intercept. Okay, the y-intercept. So that's it for the y-intercept. And for the x-intercept, it's extremely similar, okay? I guess by now you should be knowing what to do. For the x-intercept, what you do now is make the y equal 0, okay? Why? Because look at these x-intercepts, this and this. What values of y do they have in their coordinates? What values of y? 0. Can you see? 0 and 0. So if you give this equation in the y, the value of 0, and then you solve that equation, you're going to get the possible values of x for that particular value of y equals 0. That's how this works. So let's do it. I'm going to give y the value of 0 in this function or this equation. 0 equals x squared minus 1, then 0 equals x squared minus 1, then 1 equals x squared, simple algebra, okay? Then we take the square roots in both sides. Remember to apply the plus and minus. And so we have that x equals plus and minus 1 because the square root of 1 is 1. And don't forget the plus and the minus. When you take the square root of a number, don't forget always to place both answers, the plus and the minus. So we get the two answers that we expected already. The x-intercepts, sorry, are 1 and minus 1, as I told you before. 1 or 1 comma 0 and minus 1 or minus 1 comma 0. And that's it, guys. That's how it works. You have been doing this already, okay? You just didn't know that you were getting the intercepts, okay? It's very simple. So for the x-intercept, we make y equals 0. So that's it. For the intercepts, we are done. Now let's check about the symmetry of this function. What type of symmetry does this have? You know it right away, right? Just by looking at the graph. Just by looking at it. It's very simple. This function is symmetrical with respect to the y-axis. Now, how do we confirm that by means of analysis? The test is this. F is symmetrical. I'm just going to write this. With respect to the y-axis if the following happens. If and only if, remember, if and only if. If f of x equals f of minus x. What does this mean? Well, what is this? Okay, I'm gonna do it and you're gonna understand. So what is f of x? F of x is equal, according to this, is equal to x squared minus 1, right? That is f of x. F of x equals x squared minus 1. And what is f of minus x? I'm gonna write it in here. F of minus x is equal to the following: minus x to the square minus 1. Make sure to understand what I did. Okay, I'm evaluating f in minus x, and this is what I should place, right? Look at the function. Okay, so f of x is equal to this, and f of minus x is equal to this. Now, if I make a little, if I do a little algebra here, this is going to imply the following: that f of minus x is equal to minus x to the square. But remember, when we square a negative number, okay, like this, in the end we will get a plus, right? Minus x to the square is exactly the same as x squared minus 1. This is exactly the same as this, exactly the same. All right, so in the end we arrive to this, that f of minus x is equal to x squared minus 1, and also f of x is equal to x squared minus 1. So as we can see, both of them are the same. F of x and f of minus x, they are the same. They are x squared minus 1. Okay, so in fact we can write that f of x equals f of minus x. Okay, and therefore we say that the function is symmetrical with respect to the y-axis, because this test checked, was confirmed. All right. Now, is it symmetrical with respect to the origin? No, that's quite clear. Okay. Okay. Next one. This function, a little more complex function. Again, I'm already labeling the intercepts. Can you see? This is an x-intercept, -2. This is another x-intercept, 0. And it's also a y-intercept. Can you see? 0. And the other x-intercept is 2. So let's get the intercepts by means of analysis in analytical ways. First, let's write this in this way. Okay, y equals x to the cube minus 4x. And then let's get first the y-intercepts. I'm just going to write this. So for the y-intercept, what do? We make x equals 0 in the function. So here we go. 0 to the cube minus 4 times 0. And all of this, in the end, will be 0, right? So that's it. We're done. The y-intercept is 0, as you can clearly see over here. So we are done with the y-intercepts. Now, I'm going to erase this again. I need more space. Now let's get the x-intercepts. I'm going to write x-intercepts. I need to make y equals 0. So let's do it. In this equation or this function, I'm going to make the y equal to 0. So there you have it. I continue writing my equation and I try to solve it. Now I know that at this point maybe you haven't been taught how to solve cubic equations. And for some of them it's actually quite simple. For some of them, like for example this one. Why? Because you can do this. Look, you can factor this binomial in this way. Can you see what I did? I factor an x. They have an x as a common factor. These two terms have x as a common factor, and I just factorized in this way. Okay. Then, since I have a multiplication of x times this binomial, and that multiplication is equal to 0, that means that either x equals 0 or x squared minus 4 equals 0. Okay, that is a very simple algebraic property to understand. When you have two, I'm going to write it in here. When you have two numbers multiplying one another, a times b, and the result is equal to 0, then clearly either one of them is 0 or the other has to be 0, right? It's the same here. I'm multiplying x times x squared minus 4. I'm multiplying two numbers, and the product gives me 0. Therefore, what is the conclusion? That either x is equal to 0 or x squared minus 4 is equal to 0. And we already found one intercept, as you can see. X equals 0, which is this. This is the simplest x-intercept. And the other two x-intercepts, which are this and this, are going to be obtained by solving now this equation. Okay, so let's continue only in this part. So what do we get? We get this. X squared equals 4. Then we take the square root from both sides and we get this. And finally we get this, because the square root of 4 is 2, and don't forget the plus and minus. So that's it. The other two x-intercepts are 2, positive 2, and negative 2, just like we knew from just looking at the graph. Can you see? Negative 2 and positive 2. So these are the other x-intercepts. So this function has one y-intercept and 3 x-intercepts. Perfect. So try to remember what I did in here, okay, in order to solve this cubic equation. I'm going to put one or two examples like this in the activity section, okay. In this case, for this type of cubic equations, it's actually easy to find, okay. For some other, for example, if I gave you this cubic equation, x cubic minus 2x squared plus 4x minus 1. When you have all the terms, the cubic, the square term, the linear term, and the constant, this is very hard to do by hand. Extremely hard, extremely hard. Okay. Okay, so that's for the intercepts of this function. Now, what about the symmetries? Is this function symmetrical with respect to the y-axis? No, that's clear from the graph. Can you see? It's clear. But it is symmetrical with respect to the origin, because if you fold it, like I showed you before, first about the y-axis and then about the x-axis, you will find that the branches coincide. And in this case, like I said before, sometimes it's hard to tell whether when you do that visually, the branches are going to coincide. Okay, sometimes it's easy, sometimes it's hard. But how do we know for sure? How do we know for 100% sure? Okay, let's apply the test for symmetry with respect to the origin, which was this. F is symmetrical with respect to the origin if and only if, and remember, this is another symbol for if and only if, these two symbols are equivalent, okay? And they are symbols for equivalency. How do you like that? Okay, so F is symmetrical with respect to the origin if and only if we have the following. That F of x is equal to negative F of minus x. It looks very similar to the test for symmetry with the y-axis, but it's not. We have a negative in there, okay? So let's see. How much or what is f of x? Let's write it here. F of x is equal to x cubic minus 4x. Fine. And how much is f of minus x? Let's first calculate f of minus x. So I have the function here, and I'm going to evaluate in minus x. So I'm going to do that right now. Minus 4 times minus x. Okay, this is f of minus x, all of this. Now I'm going to do a little algebra here. Minus x to the cube will be minus x to the cube. Because when you multiply the sign, the negative sign 3 times by itself, you're going to get minus times minus plus. And then that plus times another minus will give you minus. Okay? So that's why minus x to the cube is equal to minus x to the cube. And then we have minus 4 times minus x. You will get plus 4x. So this is f of minus x, all of this. So clearly, f of x, which is all of this, and f of minus x, which is all of this, they don't look the same. They are, in fact, not the same. But the test doesn't want you, doesn't expect them to be the same. They expect f of x to be equal to the negative of f of minus x. The negative of f of minus x. So now let's calculate the negative of f of minus x. Basically, what I need to do is multiply both sides of this equation by minus, right? If I multiply this by minus, I get the negative of f of minus x. And if I multiply this by minus, what do I get? X to the cube minus 4x. Can you see? This is minus f of minus x. All of this. And if you can see, it is exactly the same as f of x. F of x is equal to this. Look at it. And minus f of minus x is equal to this. And they are, in fact, the same. So for this particular function, this test checks, and therefore we can affirm that this function is symmetrical with respect to the origin, because this test checked or was confirmed. And that's how you do it analytically, guys. You have to check either one of the tests, and if they check, that means that the graph is either symmetrical with respect to the y-axis, or symmetrical with respect to the origin, like in this case. Because sometimes it's hard to tell by looking at the graph. Sometimes it's hard, and this is the bulletproof way to know whether the graph is symmetrical with respect to the y or the origin. Okay. Next, this function f of x equals x squared minus 3x plus 4. You have the graph of the function right here, and we have the y-intercept, which is 4. We know that right away just by looking at the graph, but we want to do it analytically. Okay, this is just for confirmation. The graph is just for confirmation. Suppose that you don't even have, suppose that I tell you this on the whiteboard, this function, and I just ask you, please can you tell me the y-intercept of this function, and I don't allow you to graph it. You don't have no calculators, no nothing. How are you going to know that? What y-intercept does this have? By analysis, by complete analysis. So let's do it. And by the way, this is, as you can see, this function will not have an x-intercept because it doesn't cross the x-intercept. Let's see how the mathematics, the analytical part of the mathematics tells me exactly that. Okay, so first the y-intercept. What do? We make x equals 0. I forgot to write the function in this way. Okay, so let's give x the value of 0. Here we go. Y equals 0 to the square minus 3 times 0 plus 4. And then we do some arithmetic. This is 0, this is 0, and we just get 4. That's it, guys. Can you see how simple it is? Y equals 4. Like we knew just from looking at the graph. Okay, so that's it for the y-intercept. Now let's get the x-intercepts. For the x-intercept, we try to make y equals 0. Again, I forgot to write the function in this way. Okay, so let's make y equals 0. Let's do it. 0 equals x to the square minus 3x plus 4. I'm gonna flip the sides. X squared minus 3x plus 4 equals 0. It's the same thing, okay? And now we try to solve this equation. Okay, it's a quadratic equation, and when you fail to find a factorization to solving this equation or something, you can always use the quadratic formula. Okay, so I'm gonna use it. X will be, I'm just gonna write it down. Make sure that I'm doing the right thing, okay? By now you should have memorized this formula, okay? It's a very common formula, you need to memorize it. Okay, so these are the solutions for this equation, all of this. Now I'm just gonna do a little simplifications. Minus times minus 3 is 3, plus minus 3 squared is 9, and then minus 4 times 1 times 4 is going to be minus 16 over 2 times 1, which is 2. Next, x equals 3 plus minus the square root of what number? 9 minus 16. How much is that? 9 minus 16 is going to be minus 7, right? Over 2. And that's why, listen guys, that's why this function doesn't have any x-intercept, because look at this solution. Okay, look at these these solutions. The problem is this, that this number is not a real number. The reason, what is the reason? This negative radicand inside an even root. Can you see? Can you see? This is not a real number. This is not a number that should appear on this axis. This is the axis of the real numbers, right? So basically we do get two solutions, okay? We get 3 plus the square root of minus 7 over 2, and the other solution is 3 minus the square root of minus 7 over 2. So we get two solutions, but these are not real numbers because of this. These are not real numbers, and so we say that this function doesn't have x-intercepts in the real numbers. So since I told you before that these are the only types of numbers that we are using at this point, then we say that this function does not have x-intercepts. Okay, and that's clear from the graph. It never crosses the x-intercept, and analytically this is what you would get, something like this. Okay, now for the symmetries, it's very clear that this is not symmetrical with respect to the y-axis, right? This is the y-axis, that's clear. And it's also not symmetrical with respect to the origin. So if you wanted to test this function for either the test for symmetry with respect to the y-axis, which is this is the test for symmetry with respect to the y-axis. If you try this test on this function, it's not gonna check. And if you try the test for symmetry with respect to the origin, which is this, it's not gonna check. Okay, so what this is telling you is that this function is neither symmetrical with respect to the y-axis and neither symmetrical with respect to the origin, which is perfectly fine. Most functions are not symmetrical with respect to anything. Most functions. So when you find a function that is symmetrical with respect to the y-axis or the origin, that's a very good thing, because it has a peculiar characteristic that makes it more manageable, so to speak. Okay, one more. Let's do one more. This one. F of x equals minus 2x plus 2. Again, very quickly, in under a couple of minutes. For the y-intercept, what do? We make x equals 0. So let's do it. Y equals minus 2 times 0 plus 2. Then y equals minus 2 times 0 is 0 plus 2 gives me 2. This is the y-intercept. Does this check with the graph? Let's see. Yes. Can you see? This is the y-intercept. 2 or 0, 2. So you see the analysis is always correct. Now the x-intercept, very quickly, 2. We make the y equals 0. So let's do it. 0 equals minus 2x plus 2. Then 0 equals minus 2x plus minus x. Then we divide both sides over minus 2 in order to isolate the x. And then we get 1 equals x. So this is the x-intercept. Does it check with the graph? Yes. Okay, as you can see. So this is how you do it, guys. And by the way, this is also not symmetrical with respect to the y. That's clear. Neither with respect to the origin. Okay, so as I was saying, the analytical method to find intercepts and to check for symmetry with respect to the y-axis or the origin is always the best way to go. It's not the fastest, okay, because sometimes just by looking at the graph you can quickly see all these things, but first of all, I mean, you will not always have the graph at your disposal. Okay, you have to have an application that can do it quickly, because if you try to do it by hand, you know, the graph and all, this actually would be much faster than doing this by hand. Okay, so the analytical method is preferable over the graphical method. Actually, you know, most top mathematicians always prefer analysis over visualization, although they help themselves with visualization. Okay, don't get me wrong, we always get intuition from looking at graphs and so on, but the real mathematics happens when you do the analysis. Okay, because sometimes the graphs can be extremely hard to read sometimes, and the analysis is always there for you to help you out to solve any possible problem. In this case, finding the intercepts and finding whether the graph is symmetrical with respect to the y-axis or with respect to the origin. Okay, I have one more to go, but I think that's enough. Okay, I think you get the idea. It's a very simple thing. And remember, we're gonna go into the part 3 of this topic. I'm gonna tell you about local and global minima and maxima, because I just found a new software that's gonna make that easier to understand. That's what I was trying to tell you at the beginning, and I'm learning how to program it. It's pretty cool. I hope I get it nice, and so I can teach you that concept and you can get it very well. So that's it, guys. Thank you.